Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video on Math Basic Course. And as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Stepping aside as we jump into section 5.6 in the Big Ideas Math Integrated Math 2 textbook on binomial distributions. Now, I know what these are, but I'm curious to see how the book handles it, because the only thing, honestly, generally, the only thing that I do when preparing for these slide things is I import them, I make sure that they'll fit in the right spots. I see how many problems there are, and I need to know that because I have to type the thing at the bottom, and I look at the title, and basically that's the extent to where I know what it is. So we have very few, actually, let me look. It was very few. We have 22 questions to deal with, and I feel like that's very little for what they can do on the subject matter. So I question how deep this book or this chapter, this section will go into binomial distributions, because they could get huge into them, and it doesn't seem like it's going to necessarily be massive, which is fine. So very interested to see what they do with it and what they're going to teach you and what I can now then do to support and give you the solution guide for the problem set. If you want to follow along, jump down to the description section down below. You can download the PDF and find the timestamp for the part that corresponds to your learning. Without further ado, guys, let's go ahead and let's get started on this thing here. Let's go ahead and we will say you'll learn how to construct and interpret probability distributions and binomial distributions. What are those? Hopefully they'll tell you. If not, I'll expand on it. Some core vocabulary here. Random variable, probability distribution, binomial distribution, and binomial experiment. Histogram previous. I don't know when we did histograms. And, oh yeah, that makes sense. We're going to do histograms. Okay, we're probably going to do histograms, which means I probably need to get some drawing tools ready as well. I don't remember when we did them, though. Maybe from a different book. A random variable is a variable whose value is determined by the outcomes of a probability experiment. For example, when you roll a six-sided die, you can define a random variable x that represents the number showing on the die. So the possible values of x are 1, 2, 3, 4, 5, and 6. For every random variable, a probability distribution can be defined. So here's the thing, right? We can land on any of these numbers, and we look at the probability being equal likely outcome for any of these things. But there's more to the story that we're going to talk about here in a second. A probability distribution is a function that gives the probability of each possible value of a random variable. The sum of all the probabilities in a probability distribution must be 1. So here's the thing, right? We break down how anything is likely to happen. Not everything is equally likely, but as far as these ones, landing on a 1 is equally likely as landing on a 5, etc. So there's the breakdown of that. Now they say that the probability has to add up to 1, and it's something that I've mentioned for you guys before as well, that you have a 100% chance of something occurring within your breakdown, whether it's this thing or that thing, etc., and it must add to 100. It can't be less, it can't be more. So 1/6 plus 1/6, etc., 6 times is indeed 1, which would represent the 100%. Now we'll construct a probability distribution, and so they're going to do something else with this. Let x be a random variable that represents the sum when 2 six-sided dice are rolled. Make a table and draw a histogram. Here's the histogram below. Draw a histogram showing the probability distribution for x. So first thing they do is make a table. And so the idea here, and I don't see how they show the outcomes themselves, but we've seen it before. There's only one possibility that you can get a sum of 2 from your dice. That's if you roll a 1 and another 1. And same with the 12. You can roll a 6 and another 6. There's only one possible outcome. You can see it leans more toward the middle because 7 can be rolled by a 3 and a 4. A 4 and a 3, a 2 and a 5, 5 and 2, I can't do my numbers right, a 1 and 6, or a 6 and 1. So there's 6 different ways that you can roll a 7 as a sum, which is the most likely outcome, the most likely thing occurring. And it goes up to that, and it goes up to that. And yes, there actually was a problem where we did do this thing. Actually, is this what they're saying? These are listed on example 3 on page 282. Okay, yes, this was before this page 320 here. So we did do this once before as a problem, and we did see the diagram of it. Anyway, point being is there are more ways that you can roll a 7 than there are that you can roll a 2, 3, etc. That's why certain games have, 7 as the whatever, like that. And they have a histogram showing that as well. Now, a histogram is basically a frequency chart, how often things occur, and they're showing it in a probability sense, not by number of, but probability of. Because there are 36 different sums that you can, not sums, there are 36 different ways that you can get a sum from your things. 6 out of 36 is 1/6. That's the highest probability you can get from this. All the other breakdowns kind of show that lean up into that by the sum of 2 dice. There's the histogram. We're going to have to draw some of these. I don't know if it's going to take a while for me to draw them or how it's going to work, but Just be ready for those things to occur. So they draw a histogram of it, shows the frequency of it. You can see that it normalizes there. And yeah, I don't know if we have to interpret it. Oh, here we go. I thought part of the problem was interpreting. Use the probability distribution in example 1 to answer each question. What is the most likely sum when rolling 2 6-sided dice? 7. So what is the probability the sum of the 2 dice is at least 10? Is at least 10. So there are different ones that we can have that can land on 10 or more. That's 10, 11, and 12. And you add up those 3 probabilities because it's an or case. At least 10 means 10 or 11 or 12. Okay. So probability of 10 is here and 11 is here and 12 is here. They are mutually exclusive. And that probability goes to about 16.7%. Looks like we're going back to percentages. Percentages are back on the menu, folks. All right, I'm going to skip this monitoring progress one. Let's look at binomial distributions. Of course. One type of probability distribution is a binomial distribution. And that's what the name of the section is, by the way. You can see right here. So that's the heavy-hitting stuff that I expected more of. A binomial distribution shows the probabilities of the outcomes of a binomial experiment. So, okay, they're going to lay out what it is. They even show the formula. I'll see how long I need to lay down this law here and stay on this page. We'll see if it's going to be a while or not. A binomial experiment meets the following conditions. There are n independent trials, n being the number of trials that you do. There's going to be coin flips or something like that, right? Each trial has only 2 possible outcomes, success and failure. So either you get it or you don't. It either happens or it doesn't. This could be landing on heads versus tails, making a shot versus missing it, having a boy versus a girl. It's either a yes or a no in that scenario. And you can do like land on odd, not land on odd, so odd and even, things like that. It doesn't have to just be 2 numbers. But, you know, the 2 outcomes are success and fail and how we'll refer to that. That's what makes it binomial, too. The probability of success is the same for each trial. The probability is denoted by P. The probability of failure is 1 minus P. I might put the letter Q every so often just to give a simplification version of that. So you're successful by probability of P, failure by probability of Q, which is 1 minus P. If you're not successful, you are failureful. If you don't succeed, you fail. And success plus failure has to be 100% of everything. Either you make the shot or you miss the shot. That accounts for all 100% of shots. For a binomial experiment, the probability of exactly k successes in n trials is this. Now, this formula is going to look very wonky, and there's no real way that I can do it any simpler than this. They will show formulas within these things. They will show examples with these formulas, so there's less letters. Everything's going to be a number except for the letter C, because C stands for combination, and we just came off of combinations to be able to do this, and we can use the calculator to help us if we have to. But n choose k times p to the k times 1 minus p to the n minus k power. I feel like I don't want to give examples of this stuff until they give the examples and I can interpret them for you. There is very much a reason why this thing occurs the way it does, and we can even do it in the dice roll problem. We could see why the probability of landing a 7 is 1/6. However, the other version is not being a 7 because it's got to be a binomial. So with that being said, let's go ahead and see what some examples are. I'll keep this formula in mind. Now, here's what the formula says. N choose k times the probability raised to the k power, probability of success raised to the k power, times the probability of failure raised to the n minus k power. Really hard for me to interpret right now without doing some examples with you. Constructing a binomial distribution. According to the survey, about 33% of people ages 16 and older in the U.S. own an electronic book reading device, or e-reader. You ask 6 randomly chosen people ages 16 and older whether they own an e-reader. Draw a histogram of the binomial distribution for your survey. So n is going to be 6 in this scenario. We talk about the independent trials. There are 6 independent trials in this case. There are 6 individuals who were asking about something. And we're asking, what was it? Whether they own an e-reader. Now, 33% of people ages 16 and older own an e-reader. So we're expecting, what's the probability that exactly 0 of them own an e-reader, that exactly 1 of them do? Of the 6 that we ask, what's the probability that none of them do, that 1 of them do, 2 do, 3 do, 4, 5, and 6? Now notice the formula that they're using here. It's going to be this n choose k. Now n is the number of trials, number of people. So we ask 6 people. choosing 0 of them, not we're choosing, that's the combination. Choose 0 of them times 0.33 probability of success to the 0 power times 0.67 probability of failure, I'm calling that Q, 1 minus P, to the 6th power. So here's what they're actually doing on this thing, and they're going to do it for all the other ones. The 0.33 to the 0 power says, what's the probability that none of the people own an e-reader, given that 33%, they have a 1/3 chance of owning an e-reader. So what's the probability that this person, that nobody does, in this case, which means this person does not, and this person does not, and this person does not. You're basically doing 2/3 times 2/3 6 times, because it's this person doesn't, and this person doesn't, and this person doesn't, etc. Now, the 6 choose 0 represents the number of different ways that you can arrange 6 people, order doesn't matter, 6 people to not have an e-reader and no people to have an e-reader. There's only one way to do that. When we get into k equals 1, the 6 choose 1 is the number of ways that you can get one person to own an e-reader and 6 people to not, 5 people to not. And there are 6 different ways, not 6 different ways, but there are 6 different versions that you can have that as well, right? You can have the first person own it and the other 5 not, or the second person own it and 1 through, like that. So there's 6 different ways to do that. The probability of success, 1/3. So there's one person who owns an e-reader and 5 people do not. So what's the probability that one person does and this person does not, and this person does not, this person does not, this person does. So that's why the formula is working the way that it is. Anyway, they compute these probabilities, and remember, these are decimal equivalents of percentages. These can be represented in a histogram, a frequency chart, and you can see that it's most likely that if you ask 6 random people, given that there's a 1/3 probability, 0.33, 33% probability, that they own an e-reader, it's most likely you're going to get 2 people that do. It's very unlikely you're going to get 6 or 5, or 4 in this case. 0, it's possible. So it leans closer to the number that represents the percentage itself, right? 2 is, 2 out of 6 is 1/3, and this probability was 1/3. So it makes sense that it leans toward that too, in essence. Anyway, they do the breakdown of all those. We're going to have to do the same thing. And it's something where I might be able to use the calculator and kind of do more of a spit it in my formula thing and see how that works out. All right, interpreting a binomial distribution. Here we go. Use the one from example 3 to answer the question. What's the most likely outcome of the survey? That 2 people will own an e-reader is the most likely outcome. That's what they're saying here. What's the probability that at most 2 people have an e-reader? So at most 2 means 2 or 1 or 0. Now, there's a phrasing in here, and this is the part where I don't think they're going to expand. This is not a statistics class. They don't expect you to have a certain calculator. There are binomial distribution functions such as these, and there are things called binomial cumulative. This is a binomial probability distribution function. There's a binomial cumulative distribution function as well. At most 2 would mean 2 or 1 or 0, and that'd be adding those up. And you take the cumulative set of adding these 3 together. Now, they're going to be doing that, but I'm sure they're not going to be saying the word cumulative. But notice they're going to take the probability of 0 people doing it plus 1 plus 2. 0 or 1 or 2 is at most 2. You have a 68.6% probability that 0, 1, or 2, that at most 2 people own an e-reader. Okay. So it's quite an interesting go, and we're already done with the examples, which they do not get deep into it. I'm sure the problem set's going to ask some tricky questions here or there. They might even bring up cumulative natures. But let's go ahead and dive into the vocabulary and core concept check. What is a random variable? I already know how to answer that. I know what it's representing. I don't know how to give you a good definition. A variable that represents all the different outcomes, all the different possible outcomes in a distribution of probabilities. This is the part I don't really know how to say. In a distribution of events. I'm not saying this well. I'm not good at defining this. I'm good at knowing what it is when it's there, but not saying what it is. That's a bad answer. Don't write that one down. Just go back in the video or in the PDF and find out what it says. All right, give an example of a binomial experiment and describe how it meets the conditions of a binomial experiment. So I mentioned a few of them. I can talk about something like, let's see. I'm sure they're going to use those because that's why I said them, that it's common they do. Let's talk about um, uh, fine, I'll say it. Making a basketball shot. Making a basketball shot. So here's why it meets the conditions. You can have a certain number of trials that are all independent. So one, all trials are independent. That means making one shot, and this, you could argue this isn't necessarily the case, right? If I miss a shot, I'll go, oh, I missed to the left, or I missed too far. I should, weaken my shot a little bit more like that. But, in a vacuum of shots, when you see them, they're independent. So all trials are independent. All your shots are independent. It satisfies a binomial condition. It satisfies the binomial condition. It satisfies the fact that either you make the shot or you miss it. And I don't know what the other thing is that we have to state, but those are the big things that I know. Hold on, what's the other one? Let's go back. The probability is the same for each. Oh, okay. Well, I thought that was the independent portion. So the probability is the same for each trial. So yeah, that's what I thought that had to do with the independent part. So again, if you have a 60% chance of making a shot, then it's the same thing. Let's not just say a basketball shot. Let's say a free throw. That way you're on the line, in the same way. Otherwise, in some cases you're guarded. In some cases you're farther back. In some cases you're on the side. So I'd rather do making a free throw shot. Okay. All right, and I'm sure that's going to be some kind of question on here. It's a very classic one to do. So is like making a shot in soccer or something like that, or having children, boy or girl, stuff like that. So, guys, we're going to go ahead and get started on these. It's just numbers 3 through 22 to do. I'm going to take a sip. I'm going to go ahead and get started. It already says draw a histogram, so I have to find a way that I'm going to make the table, not the table. It does say make a table, actually. Shoot. Okay, well, maybe I should create every time and pause and put in just to get the graph things ready. We'll see. Maybe I'll create it with you to say this is how I do it, and after that we can do it that way, or I can use that as a template. Make a table and draw a histogram showing the probability distribution for the random variable. X is the number on a table tennis ball randomly chosen from a bag that contains 5 balls labeled 1, 3 balls labeled 2, and 2 balls labeled 3. All right, as far as the table goes, we're going to do some form of X and P of X, probability of each thing occurring here. There are only 3 different things. So 5 balls labeled 1, 3 balls labeled 2, and 2 balls labeled 3. Now, 5 plus 3 plus 2 equals 10. There are 10 balls total. If there are 5 of them that are labeled 1, you have a 1/2 chance of that occurring. I'm almost inclined to sometimes put the decimal, like in this case here, because that's 0.5, 50%. It's easier for me on the histogram chart to label that. Maybe I'll do that in kind later. 3 balls labeled 2, so 3/10 is just 3/10 there. And then 2/10, 2 balls labeled 3 is 1/5 here. So there's the table of the breakdown of that. And then they want us to draw a histogram. So yeah, with the histogram here, I'll do like 2 axes. This one is for the number of balls per with the label of each ball, and this is the probability of each. This is where I got to get a little creative. 1, 2, 3, 4, 5. Actually, that'll work pretty well. This will be 1/2. That's 5/10. Here's 4/10. What's that? 2/5. 3/10. 2/10 is 1/5, and 1/10 is 1/10. I don't know. I don't know how I want to do this each time given that. Anyway, so with the histogram, it's spread out among labels of these balls. There's 1, 2, and 3. And for 1, let's see, I'll use my rectangular thing here. Yeah, I should have prepped for this in a way. I should have anticipated this would happen. For 1, we are going to go to the 1/2 mark like that. For 2, we're going to go to the 3/10 mark. And for 3, we're going to go to the 1/5 mark, like that. So there's our spread of this. I think that's it for the question. I think that's all they wanted. So, yeah, there it is. There we have it. No interpretation, nothing else like that after. All right, number 4. C equals 1 when a randomly chosen card out of a standard deck of 52 playing cards is a heart, and C equals 2 otherwise. So this is kind of a binomial distribution, right? So there's C and probability of C occurring for our table. It's either a 1 when it's a heart or a 2 when it's not a heart. There are a quarter of the deck is broken up into quarters of their suits. So a quarter of them are hearts, 1/4 of them are hearts, 3/4 of them are not hearts. So we'll just kind of do it like that. We don't need to actually put out of 52, even though it's 13 out of 52 and 39 out of 52. That's not necessary in this case here. It's not necessary. So here for P of C, meaning probability of it being a heart versus not a heart, I think this time I'm actually going to do the well, never mind. We'll do this 1 and 2. 1 and 2 for C, all things C. This will be, I'll just do it like this. We'll do 1 3/4 and 1/2 and 1/4. So we won't actually reach the 1 at all. So 1/4 of them are hearts. 3/4 of them are not hearts. Like so. All right. There's your histogram. They're big bar graphs. I don't think I have to make them that big, but I did. Number 5. W equals 1 when a randomly chosen letter from the English alphabet is a vowel, and W equals 2 otherwise. I believe we're assuming in this case Y is a consonant, not a vowel. So there are 26 letters in the alphabet. So in this case here, we're going to do W and probability of W. So 1 and 2. I'm kind of glad they're not big histograms and a lot of things I'd have to do. So when it's a vowel, that's 5 out of 26. A, E, I, O, and U are those. And then we have 21 out of 26 when it's not a vowel. So let's bring this one kind of up again so I don't have to do too much. I'll erase what I need to. So we got the 1 and the 2. We'll call this P of W instead. We'll call this guy W. Okay. So, yeah, we need this breakdown here differently. Let's do out of 26. That doesn't break down very well. 1, here's 1/2. Whatever. We can still do it like this because 5 out of 26 is a little less than a fifth, which is less than a fourth. It's probably kind of like that ish. I'm still good on using that aspect of it. 21 out of 26 is the kind of opposite of that. If I do, see, this is where using this in the calculator is helpful. But 21 out of 26 is it's around 80% because it's a little more than 4/5. It's around 80%, which will be more than 3/4, kind of like that. So 80% of the way. So maybe not perfect. Maybe I should have broken them up by fifths instead, but that's still the concept of what we're doing. So here are all of the consonants. Here are all the vowels. Okay, and number 6, n equals the number of digits in a random integer from 0 through 999. So, interesting. Okay, so in this case, n and p of n. So how many digits can we have? 0 is still 1 digit. So you can have 1 digit, you can have 2 digits, you can have 3 digits. How many numbers are 1 digit though? 0 through 9, that's 10 digits out of the 1,000 numbers represented. Make no mistake, 0 through 999 is the same as 1. That's 1,000 numbers. So 10 over 1,000 is 1 over 100. There's only 1% of them that are single digit numbers. Double digit goes from 10 to 99, which is 90 numbers from 10 to 99. So we have 90 out of the 1,000 here. That's 9 out of 100, which is 9% of them. And then the rest are the rest. So the rest should be from 100 to 999, which is 900 of them. So 900 over 1,000, that's cool. Which is 9/10, which is 90% of them. So let's break it up that way. Given that we have that, let's do I probably got to make a new histogram here. Shoot. I want the lines. Let me copy and paste this on the next thing because I want the lines to help me draw and make up my own histogram there. Okay. I'm going to go by, let's see what you can see on here. Let's do 5 lines. And let's do n. I'll keep it skinnier this time. So the numbers are 1, 2, and 3 by the number of digits, n and p of n. This will be 100%. This time I'm going to do, I don't know, they've been doing fractions. They're doing fractions on the bottom of there as well. I guess I'll keep doing fractions. So 5/5, 4/5, 3/5, 2/5, and 1/5. And broken up evenly here. 1, 2, 3. So 1, 2, 3. Okay. So 1 is 1/100th. Now that's going to be, I'm just kind of making it what it is, but 1/100th, 1% of, or, I got to go 1/20th of the way up. So basically like that. 1/20 of the way up to 1/5. So that's just the 1%. 9/100ths, that's still not even halfway up to 1/5. Because, yeah, it's just not. So that's going to be a small guy there as well. It's not even halfway up to 1/5. 1/5 is 20%. 9/10 is 9%. So not quite halfway up. And then we have that which makes 90%, which is halfway between 80 and 100. So there's 80 and 100 like that. And this becomes those things together. So that should be that histogram. Did I interpret that right? Number of digits? Yes, yes, yes. Okay, there's the breakdown. Let's move forward. In exercises 7 and 8, use the probability distribution to determine the number that is most likely to be spun on a spinner and the probability of spinning an even number. All right, number 7, we have the histogram, the distribution. Number most likely to spun on a spinner. So on part A, 2, we'll say X, 2 is the most likely number to be spun. It's the highest frequency. Probability of spinning an even number. Probability of even will be probability of landing on 2 plus 4. It's 2 or 4 in this case, and we add both of those. Probability of 2 is 1. So this is half of a quarter, which is 1/8. And that's 2/8, which is 1/4. This is 3/8 here. 3/8. Don't think it's 1/3. Don't think it's 1/3. So it's 3/8 plus, and then the 4 is 1/4. Now 1/4 can also be written as 2/8. So that's 5/8. 5/8 probability. If we want the decimal, that's 62.5%. I know my 5/8 decimal. I know my 8ths decimals very, very well. So 62.5% likelihood of landing on an even number based on the spinner. Number 8. Same 2 questions, right? So probability, or the highest, okay, the numbers on the spinner this time are 5, 10, 15, 20, and 25. There's no in-betweens there. So for part A, the most likely thing to land on here is 5. Probability of being an even number, I suppose we're just looking at the 10 and the 20. So half of 1/6 is 1/12. That's what this part represents. And that's the only one that I really care about because I'm looking at the 10 and the 20 numbers. 10 is on 1/6. So probability of even equals probability of 10 plus probability of 20. One or the other. Probability of 10 is 1/6. Probability of 20 is 1/12. So that's 2/12 plus 1/12, which is 3/12 or 1/4. And 1/4, as we know, is 25%. So I hope that just me writing X equals for the other thing is going to be valid enough for what it is that we're actually doing on those situations. But yeah, I feel good on those ones. So X equals 5 and as we move forward. Okay, let's go to number 9. Hold on. Number 9. 9 through 12. Calculate the probability of flipping a coin 20 times and getting the given number of heads. Okay. This is where we're starting kind of the binomial distribution function stuff, or at least it could be, and how we're doing it, and I want to this way. So either we land on heads or tails. So in this case here, n is 20. We're going to flip it 20 times, 20 independent trials. The probability of landing on heads is 50% or 0.5. Probability of landing on tails is 1 minus 0.5, which is also 0.5. Our formula is going to be, and I forget how they write the first part, the whole, like, what this whole formula thing equals. I think we can say probability of whatever we're doing. Probability of one head, this is going to be small. Probability of landing on exactly one head is going to be take 20, choose 1, multiply this by probability of success, that's 0.5 raised to the first power. You're going to have one time landing on head, and landing on tails, 0.5 to the 19th power. That's 20 minus 1. So we're going to be computing that. Don't expect to not use a calculator here. This is exactly, it's totally a calculator-driven thing. So I'm going to go to my calculator for you guys, and I'll show you what it is I'm going to do. I'll show you two different things. The way that you'd have to type this out, and a feature that my particular calculator has. So 20 choose 1, oops, wrong button. 20 choose 1 times 0.5 to the first power times 0.5 to the 19th power. Now, in the case like this, it's a little mundane for me. It's because it's still 0.5 for both of them, it's going to be that same thing over and over. In different problems, we won't do that, so we're going to leave it like this. Now, the problem with this answer for us is this means to the negative 10 to the negative 5th power. Hold on, let me interpret this for you. 1.9073 times 10 to the negative. So this means this here in scientific notation. Like I said, this number's small. Now keep in mind, this is the decimal equivalent of a percentage. We could multiply it by 100 and work it out. So it's this about, this also means you'd have to shift this decimal this many places over this way. 3, 4, 5, you know, like that. So it would be very, very small. Let's actually just do the percentage equivalent, if you don't mind. So I'm going to multiply, because I think then it'll spit something out that's reasonable for us to, even though it's 0.00, whatever. So let's multiply it by 100, shift it 2 decimal places over, get the percentage version. This is the percent this time. This is the percent. This is how unlikely this is to happen. So 0.0019%. About. Like that. So very, very small, right? The likelihood of landing on heads just once out of 20 coin flips, that is rare. Don't bet on that, right? 10 is most likely, and I'm sure that's one of the questions that they're asking. Let's see if it is. Now that I go to that. Nope, 10 is not among them. And 20 is going to be even less likely. So just kind of get ready for some weird answers. Now, what I want to show you on this as well is another thing that I have in my calculator that I can use, given that it's a graphing calculator. I have something called, and I hit the second button and vars where it says distribute, and I can find something called the binomial PDF distribution function. And here's the things that we enter. We enter the number of trials, the probability of success, comma, the amount of times you want that to be successful. Now remember, this is the number that's going to give me this one here. This is the decimal equivalent. So it should be giving me that if I did it right, and it does. It lines up exactly. So that's another possibility, and I can be using that. I'll be writing the formula out, though I might be typing this in my calculator without you knowing. And I can go ahead and use that, which is pretty awesome. If you have that calculator function, you can use it too. You'd have to know how it works, but it's there. Furthermore, I might just use it as a whole on a... I'll show you what else I can do with this in a second. Number 10. This time we're going to talk about, I should have said k equals 1 in this one. In this case for number 10, k equals 4. So we're going to now say probability of 4 heads. It's going to be more likely than the others. Still not really there. Not really there. It's going to be most likely among all these. So this is going to be 20 choose 4 times 0.5 to the 4th power. That's probability of heads times probability of tails, 0.5 to the 16th power. 4 heads are landed on, 16 tails are landed on. 20 choose 4 different ways that you can get 4 heads and 16 tails. So I go back to my calculator, and I can just change that number into a 4 for myself so I can get this answer out for you. I'm going to give you the percentage version because I did on the last one. This is still less than 1%. Like I said, this is not going to be very common. 4, 6, 2, 1%. I'm trying to get the same number of decimals. 0.4621%, still less than half of a percent. And keep in mind, even if it was 10 heads, 10 heads isn't necessarily going to be 50% likely, because there are 20 different coin flips. You have to spread it out, right? The 0 heads through 20 heads is all spread out to be the 100% of outcomes. So even though 10 is most likely, and I know 10 isn't on here, let me tell you what 10 is for this thing, just to give you the heads up. 10 is going to be most likely, but it's not like it's going to be 50%. It's 17.6%. It's the most likely outcome of all of them, but for exactly 10 heads, 17.6% is it. They didn't ask it though. They are asking for 18 heads and 20 heads. So for 11, if K is 18, we're going to do the same scenario. Probability of 18 heads. Like I said, this is going to be very small. Everything's basically going to be less than 1% here. So they're really, really playing with your emotions that way. 20 choose 18. That's a 20. 20 choose 18 times 0.5 to the 18th power times 0.5 to the second power. And I want to keep reiterating that as long as both of these are 0.5, I might as well be doing 0.5 to the 20th power on my calculator. Heck, for me, I might as well just be using my Binomial PDF distribution formula. So this is going to be, like I said, very, very small. 0.0181%. And then number 12K equals 20. This is going to be the lowest of the low. It's going to be the same as probability of 0 heads. So this is going to be even lower than that first one we had. Probability of, not 0, but it is the same. Probability of 20 heads. Every single time you land on heads? No. 20 choose 20 times 0.5 to the 20th power times 0.5 to the 0 power. See, 0.5 to the 0 power is just 1, so that doesn't really change what we're doing there. So let's do this to the 20th power. And then I'll just do times 100 straight up, because I know we're going to do the percentage. Okay, even this one uses that scientific notation, so I need to do this right. I believe it's going to be 0.00009.5%. I'm going to write it like that. I believe that's what it is. It ain't happening. It's a 1 in a million. It's a 1 in a million shot. And even then, I wouldn't bank on it actually happening. Sorry, that was number 12. That was number 12. Okay, those were very little amounts. I think they're trying to get you into the idea that these little things as a whole, as an aggregate sum, may land on be 100% as a whole. But when you look at them as individual parts, they represent things very small. I'm surprised they didn't lean on ones that were a little closer to 10, though. All right, number 13. According to a survey, 27% of high school students in the United States buy a class ring. Yeah, I didn't buy one. Give me part of the 73%. You ask 6 randomly chosen high school students whether they own a class ring. We're going to draw a histogram of the binomial distribution, and we're going to answer answer the questions after. So part A is going to be all about this. We got to do that histogram thing. And I'll be honest, I'm probably going to go with this, do this very fast. So 6 randomly chosen high school students. N is 6. P is probability of success, that's 0.27. So Q is going to be 1 minus 0.27, which is 0.73. At least these ones are different this time. Now, we're going to be doing a breakdown of this thing for probability if K equals 0 all the way to, so that's nobody has a class ring, to 1 person has a class ring. We got to do all of these. 2, 3, 4, 5, and 6. There's no way around that. Even in the histogram, we have to do this. Did they say make a table? No, they said draw a histogram. I'll just do it this way. Table would have been just as fine. Now, I'm not going to show... Okay, I might write these all out here, but I'm going to do it in a very fast way on my calculator after this, which I'll show you. So we start with 6 choose 0 times 0.27 to the 0 power times 0.73 to the 6 power. That's a 0, by the way. Now, we'll get a number for that in a second. And then we'll have 6 choose 1 times 0.27 to the first power and 0.73 to the 5th power. Basically, you'll see this dwindling effect of this over and over. And I think the one thing that'll speed it up for me is if I do this and then copy and paste this down, and then I can just insert some parts. I know you're going to have to do a little bit more, but let's just do an infinite cloner. Down you go, down you go, down you go. All right, so here, isn't that fun? 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 5, 4, 3, 2, 1, 0. Oh, yes, much faster. Now, on my calculator, I can even do this a little faster as well. You technically could, too, if you do a couple things. You can use a y equals equation thing, and you can do one of two things. You can either do the formula as it is, the 6 choose whatever, but I'll make my choose be my x. That's the one variable that I need. Everything else is kind of based off that thing, right? I can multiply this by 0.27 raised to the x power, and then I can multiply that by 0.73 raised to the 6 minus x power. And I need that to be in raised to the 6 minus x power. I need that to be in parentheses. So I could do that, and I could go to my table, start at 0 and increase by 1. And this will give me all those decimal values right here. Boom. Perfect. These decimals are the decimal equivalents of percentages. I'm not going to write the percentages this time. I'll just use decimals. And these will not be, there are no real fractions that we're trying to work off of here. Technically they are, but they're so dense that we'll just use the decimal versions of them this time. Another version I could have done with my calculator here is I could use the binomial distribution PDF thing, and this will be the exact same as what you just saw in the last one, where there are 6 trials, probability of success is 0.27, and we're going to do X trials for each of them. So when you look at this table, it should give me the exact same values here as it does there. Yes, it does. So no matter what, I'm getting these values out. So please let me write these ones down. I'm going to round to the nearest, let's do 3 decimal places. So 0.151. So 15%, about 15% that nobody is going to do it. And then 0.336, about 33%, that one person is going to do what? Oh, buy a class ring. Then 0.311, about 31% chance that 2 people will. And then it goes down, like significantly more, 0.153, 15-ish again, 0.042 for 4 people. 5 people is 0.006. Remember, that is 0.6%. That's less than 1%. And all 6, that'll be 0.0004. That 39 there is going to round up to 4. So I did want to write one more decimal with that. Then maybe I should have done 4 decimal places for all of them. But there's the breakdown. We still have to do with a histogram. We still have to draw that. So I need to use those numbers as a result of it. I have them on my calculator. Hopefully you have a way to write that down. Go ahead and write those ones down. Pause this video if you'd like, because I'm going to move forward. So if K is buying a class ring and probability of K is exactly that. What's the highest? 33%. We can go by 5% increments here. No, 6. 5 is smoother for me. 5, 10, 15, 20, 25, 30, and I'll kind of go up to 35 here. The idea of it anyway. So 5%, 10%, 15%, 20%, 25%, 30%, and 35% should be above right there. Now we're going to divvy these up. I'm going to try and give equal widths. It's pretty good. 1, 2, 3. Oh, I need 0 on here. Hold on. It was good. 0, 1, 2, 3, 4, 5, 6. 3 and 4 look a little bigger. Sorry about that. Anyway, so let's do this breakdown. I have them on my calculator still, so I can do at 0 is around 15%. I'll just kind of mark it right there. Just a little above 15%. 1 is at 33%. So this is the highest one. 33 is a little more than halfway between that and 35. So like that. I hate how this thing snaps. 2, 31-ish percent. And remember what the official number was, right? 37%. So it totally makes sense that it leans toward the 1/6 to 2/6 nature of this thing, and then it starts dwindling after. I love binomial distribution things. I really do. I love the interpretation, the idea behind them, the hands-on approach with them. They're tangible. They really make sense to me. Maybe that's brand new for you in terms of exposition. I've done this a lot before in the past, but 4%. 5 was less than 1%. That was around 0.6%. So it's really getting low. And 6% you basically won't see. I won't really put anything. You basically won't see it. So it's going to look like that. That's the histogram. That was just part A. Part B. What is the most likely outcome of your survey? Well, we already saw that. That would be 2 class rings. No, 1. Ha ha ha. 1 class ring purchased is most likely. It's not that they're not asking each person how many class rings you'll buy. They're asking 6 people, multiple people, will you buy a class ring? So 1 person purchasing a class ring is most likely. What's the probability at most 2 people have a class ring? So now this is going to be probability of at most 2 is less than or equal to 2. So that'll be probability of 1 or 0 plus probability of 1 plus probability of 2. K equals 2. That's the at most 2 version of that. Now, this is approximated since we have the rounding bits. We're basically going to add these 3 up together. Because they're kind of rounded, I want to, I'm going to do that on my calculator in a different way. I actually don't know how to do it using these. I have something else I'll do. I have another feature I can do, but I was trying to find a way of just inputting it on this. I don't want to take up your time. So let's get the answer. I'll write the rounded versions of them, but I'm gonna get the actual answer. You know how I said they're binom PDFs? They're also binom CDFs, cumulative distribution functions. 6 trials, 0.27% chance of occurring, and if I put a 2 here, it's going to add the 0, 1, and 2. It's going to add everything up from 0 to there. So this is going to be the answer. So I'll first write out, so 0.7977 or 79.77%. So I'm writing that answer here. Now that's coming from adding up 0.151, 0.336, and 0.311. 0.151, 0.336, and 0.311. Those 3 added together are that. I did add an extra decimal with this thing in mind, just for, precision's sake, I have that. So 79.77% likelihood that you're going to have that. So that's a pretty cool kind of idea of breakdown and stuff, and I hope that you tangibly can make sense of exactly what we're doing on those. Okay, let's go to number 14. So 14 is very close to what we did on 13. It's just the idea of there's an odd numbered version of the problem. There's an even numbered version of the problem. According to the survey, 48% of adults in the U.S. believe that UFOs are observing our planet. You ask 8 randomly chosen adults whether they believe UFOs are watching Earth. You ask my mom, and she'll swear to this day. She just told me again about a week ago, I told you that I saw a UFO when I was a kid, right? She describes the whole story in full. She's one of them. I don't know if I believe her. I haven't observed it for myself. Anyway, or I believe she thinks she knows what she saw. Anyway, different, right? All right, let's go. 48% of adults. Shout out my mom. I love you. What am I looking for? 8 randomly n equals 8. Probability of success. It's not that you successfully saw one or something. It's just probability of success. It's just what it means. Even if you remember how I talked about basketball shots? It could say that your probability of success is the probability of missing a basketball shot. It doesn't mean that you successfully made the shot. It means the thing you're looking for, the desired outcome. Probability of failure is 0.52. So let's do the same thing as before. This time, I don't think I'm inclined to write the formula thing out each time this time. In fact, I'm going to use a table. Let's do K and P of K. and we have to get this thing rolling. So it's the same thing as last time what we're going to use. If you have the formula, you can try it out. It does take a while. That's why I'm going to streamline this a little bit more. 0, 1, 2, 3, 4, 5, 6, 7, and I need one more for 8. Don't ever forget to put 0. There could be 0 people who believe, but the truth is out there. All right, 0 to 8. By the way, half the things I see in the air are UFOs. Hey, what kind of bird is that? I don't know. Can't identify it. Anyway, these probabilities, so here's what I'm going to do on my calculator at least. I'm going to use... I'll use the binomial version of this. Let's do that one more time up here. Binom PDF. I have 8 trials. Probability of success is 0.48. And I'm going to do this X times. And we'll refer to the table as we did like last time. So starting from 0. So I'm going to use, I guess 4 decimal places may be appropriate once it gets a little small. So 0.00. I kind of want to use percentages. 5, 4. 1 is 0.0. Hold on. This is hard for me to fit. 0.0395. And then 0.1275 for 2. Okay, I'm gonna pause this as I'm writing it down. I hope that's okay. Okay, I wrote them up to 6. Let me scroll down so you can see these others and confirm you got them right. So 7 and 8. So 7 is 0.0244. Ooh, these are getting small that I'm writing. And 0.0028. I'm squeezing these ones in. So here's what I just wrote down. Squeezing those ones in. I'm going to refer to my calculator when it comes to seeing the numbers. Now, I'm seeing something that I expect. I know that they're going to be asking the question, what's the most likely outcome, things like that. But since our number lands right around 50%, it makes sense that this number is going to be the most likely one about halfway through. So I'm expecting something that's going to have kind of a symmetry, some sort of symmetry here, close to it at least. Anyway, so you have that formula you would otherwise be using, and let's go and do the histogram version of that. Most highest number is 27%, so a little more than 25. So I'll probably go by increments of 5% once more, where we have K and P of K. And this is going to be 5%, 10%, 15%, 20%, 25%. And I guess 30 would go up there, but just like last time, I'll just kind of extend beyond it because there's only one that goes up there. And then let's divide these in increments here. All right, so 0, 1, 2, 3, 4, 5, 6, 7, and 8. All right, it's a lot of histograms, man. So 0, that's 0.0054. So that's less than 0.5%. Less than half, excuse me, 0.5%, more than 0.5%. But very, very small. Very, very small. Actually, let me see it on my calculator because that number was hard to read on there. And then we have 0.039, so around 4%. So now we're going to go 4-ish% right there. The snap feature, man. It's never been good for me. Especially if you guys remember when I did them with compasses. 0.1275, so 12.75%. Listen, that's more than halfway between. That shoots up a little bit. So that's up here. About. So 12.75%. Looking a little bit like that. Okay. 0.2355. So 23-ish%. So that's really shooting up like that. Close to 24. And then the big guy, 27.17%, leaning toward that middle. 26, 27. Yeah, not bad. 20%. We're looking pretty much right at 20%. If I was any closer, I wouldn't know. Then 9-ish%. 9-ish% on that one. A little more, 9.25%. I'll dig it. Is that 2? What did I write? I have to go down here. 7.24, 2.4%. So 2.5%, about halfway between that and 5. Little less than halfway. There we go. And then 0.002. So less than 0.5% for sure. This is like 0.25% this time, even smaller than that previous one that we saw. Very hard to discern between the two, but I feel like something could still pop up on there that we could actually see, so I'm going to bring it. So there's my histogram. That is part A. So part A. Part B. What is the most likely outcome of your survey? That four people believe in UFOs? What was the question? That UFOs are observing our planet. Most likely outcome is four people. Whoa, that's small. Let's do that again. 4 people. There we go. Part C. What is the probability at most 3 people believe UFOs are watching Earth? So probability of less than or equal to 3. It says at most 3, so 3 or less. So that's 0, 1, 2, or 3. So once again, I'm going to go a little bit of a shortcut here, guys. Here's what you're going to be adding up. You're going to be adding up these 4 numbers here. Boom, 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 boom. Oh, that didn't copy. Let's do that again. Copy. Paste. So we're going to be adding up these numbers here. Plus, plus, plus. And I got my calculator to kind of help me out. So let's go to my calculator. We're going to be doing this. We're doing 8 people with a 0.48% chance of yesness and 3 or less adding up together. And it's this number here, around 0.4078 or 40.78%. Once you hit that fourth person really skyrockets to close to 70% or something like that, right? Because that's the one that's most likely outcome, and then it kind of dwindles from there. But yeah, it's rather symmetrical appearing as you see that on that. So that's part C. Okay, number 15 and 16. Describe and correct the error in calculating the probability of rolling a 1 exactly 3 times in 5 rolls of a 6-sided die. So 6-sided die probability should be 1/6. That's good. The issue lies here, the 5 minus 3 versus the 3. Now 5 minus 3 is 2, right? But if you're rolling it 3 times, then you're getting that 1/6 chance times 1/6 times 1/6. It should be 3 of them. The others should be 2. So they have swapped that whole k and minus k kind of deal. So they have the exponent value swapped in the formula. I'll just kind of keep it point blank like that. The idea is that your probability of success also shows the number of times you were successful. So probability that k equals 3 instead should be, it's 5 choose 3, that's all good, times 1/6, that's all good, but this should be the third power. And 5/6 should be the 5 minus 3 power, which is 2. So, we work it out. I'm going to go ahead and compute what that is. Here, let's turn 5 minus 3 into 2. Boom. Once again, you can type that in your calculator as needed. I'm going to, once again, show you the other version I have. I like to kind of show off this version of that and make you go, oh, I need a calculator for that. If you're going to take stats, you need one of these calculators anyway. So what is it? 5 trials. Probability of success is 1/6, and we're going to land on it 3 times. Or are we now? And that's 0.032. About 3.2% chance that it's exactly that many times instead of the 0.161, the 16% chance thing that they said. Okay, and that kind of makes sense. If you have a 1/6 chance of landing on it, then 3 of the 5 landing on that same number exactly 5 times, a 1 is not likely. Number 16. Same scenario. Oh, they didn't use the... Well, here's the thing. We're doing the same... So, correcting... Listen, I don't have anything to correct this with because I already corrected it on the previous problem on 15. On 16, they're missing the N choose C formula thing. They're missing the combination aspect of the formula. C correction above. So I'm going to go and copy and paste that. It's the same question, right? It's still K equals 3. So it's the same question that they're asking you. So you said correct the error, and we did. Now, this is not the lecture portion of things, and they never explored it, and I didn't get to explore it either. But I don't think people fully will realize, like you as the viewer, you might not fully understand why this formula is what it is. I'd love to dive into it more as a whole. Their first example they did kind of showed a table thing with it, like landing on a 7 as a sum of 2 numbers. It's most likely frequent. But we didn't get to spell it out in a tree diagram, and that's something that I'd love to do at some point. I don't know, maybe as an exploration video. Because this really has merit, and this is the shortened way of doing it, and it's really cool. But yeah, you absolutely need this because there are 5 choose 3 different ways that you can roll a 1, roll 3 ones out of your set in your arrangement. The probability is just kind of low. Anyway, let's keep going. Number 17, mathematical connections. At most, 7 gopher holes appear each week on the farm shown. Let X represent how many of the gopher holes appear in the carrot patch. Assume that a gopher hole is an equal chance of appearing at any point on the farm. Okay. Oh, carrot patch. I was like, what am I looking at? All right. So it's like areas, right? They're areas of different things. We can find probability of landing in a certain area like carrot patch. We'll do that in a moment. There's a part A, B, and C. Find probability for X equals 0 through 7. The probability of a gopher hole appearing in the carrot patch is equal to the ratio of the area. Oh, yeah, so that's what I was saying. So you find out areas. Make a table showing the probability distribution, make a histogram. Okay, so yeah. Was X the number of gopher holes? Yes, it was. So I'm going to start the next page. Let's go to number 17. And let's first find the area. I'm going to copy paste this diagram. Let's find the area of the carrot patch. And then the area of the whole thing and find just the probability of landing in the carrot patch itself. Okay, so let's do it over here. So if this, lock it in place, if that's 0.8 miles and that's 0.5, and this is 0.3, and this is 0.3 miles here, and 0.3 plus 0.3, that's 0.6 miles. The carrot patch... Did they say it's rectangular? We're going to assume it's rectangular. If that's rectangular, these are parallel. If these are parallel, this is a trapezoid. So the area of the carrot patch is going to be 1/2 the sum of your bases. You average your bases, and you multiply by height. So it's 1/2 0.9 times 0.3. 0.9 times 0.3 is 0.27. Half of that is 0.135. Square miles, I believe. I'm not going to trust myself, though. Let's do 0.135. All right, so 0.135 square miles. Now, the area of the whole thing is a length times width bit, so we got 0.8 times 0.6. I'll trust myself on this one to be 0.8 times 0.6 to be 0.48 square miles. So the probability of landing in the carrot patch, of having a gopher hole there, or whatever, the probability of that carrot patch area is going to be dividing those areas. So 0.135 divided by 0.48. Okay. It's going to be somewhere between a third and a quarter. I'm going to guess like 28%, something like that. So 0.135 divided by 0.48. And it's an exact, oh wow, 28 point, okay. 0.28125. Now, I want to leave that exact. First of all, that's an exact value that's written on my calculator, okay? Secondly, let me show you. So we're going to use that exact value. Now, I also want to do 1 minus this. If this is all about binomial stuff, it's either landing in the carrot patch or not landing in the carrot patch. It doesn't matter that there's a, it looks like a potato one and like a cabbage patch or celery, but whatever it is. So this is P. This is P of 0.28125. 1 minus that is our Q. And I'm going to write this number down, 0.71875. So there's a probability of one, probability of the other, and we can use those now to come up with the binomial distribution of having gopher holes land in there. This is, wait. Oh, that's right. Carrot patch is equally likely. It's not the probability of having a gopher hole. It's probability of being in the carrot patch for a gopher hole. Got it. Okay. I thought they said probability of having a gopher hole. Let's do it. Okay, so we're doing everything through 7. So that means we're doing 7 of these, I believe. Yeah, at most 7 gopher holes. Okay, that works. So there's 7. P is this guy. Q is this guy. And we're going to find P of X for each of these. So as a whole, not H-O-L-E, W-H-O-L-E, X equals 0 and X equals 1, etc. As a whole, we're going to be doing what we did before. I'm going to use my calculator to do it a little faster. 5, 6, 7. Yeah, this is what makes this take a while. No wonder there are only 22 questions. So we're going to do N choose K times probability, what was it? 0.28125. 28125. Probability of success raised to the K power, and probability of failure, no gopher holes in the carrot patch, raised to the N minus K power. That's going to be 7 minus 0, so 7. Now, that's going to happen for this one, and it's going to happen for all the ones succeeding it. What I am going to do is a copy-paste job of all the ones after this. So let me actually, for a second, let me erase the 0, and that. Let's copy and paste. Let's use the cloner. Infinite clona. I know you can't do this. I apologize. You're going to have to do the whole thing. Or you don't have to write the formula if you can use the thing in your calculator and just repeat it. So I'm using this to show you what it is we're going to do. So 0, 1, 2, 3, 4, 5, 6, 7. In fact, I'm going to do this. I'm so nifty. That probably took longer than writing those. And this one I have to write 7, 6, 5, 4, 3, 2, 1, 0. Now I do have to write out the decimal versions of these afterwards. So I'm going to once again go to my calculator and do the this thing where I have 7 gopher holes. This is probability of success 0.28125, and then we're going to do this x times, and that x is going to increase from 0 to 7. So I'm going to write in these numbers here. Oh, it goes to 0 really. Oh, that's not 0. Point. Ooh, I have to shift this thing over. Give me 1 second. You feel free to write these down as you see them. I'm tooling around with my thing that I wrote down. Oh, the infinite cloner is still an infinite cloner. Hold on. Sorry about this. All right, hopefully you're writing these numbers down as you see them. All right. 0.099. I'm going to do 3 decimal places. 0.099, 0.271. These are percentages, remember, or, it's like 31.9% or whatever. 319. 20.8. 0.081. 0.019. 0.002, and then 7 goes low. I have to use more things, so 0.0001 I'm going to put. So that's how I use 4 decimal places. So here's what I have for these. That's the breakdown. That's part A. Okay. Let me start to build out. I'm just going to pause. I'll build out the table and I'll fill the parts in after that. I don't know why I need a table version of exactly what we just had in copy paste job, but give me a sec. Let me just build it. Okay, I actually decided on using the grid line feature here and making the boxes like that. So, listen, I'm just going to fill these things in right here. So, 0.099. I mean, I don't know why they have me do the two different things. They're like kind of the same. 0.319, 0.208. This is very black blindness. There's a lot of like black on the screen. 0.081, 0.019. All right. And then we do have to do a histogram. So this is the part where, what's the most common one? 0.319, so the 31%. So let's go every 5 again. We do this several times here, so 5%, 10, 15, 20, 25, 30. So P of X and X, and we have to do this from 0 through 7. 1, all right, let's see. 0, 1, 2, 3, 4, 5, 6, 7. Okay, let's go. So from that, we have 9 I have to write these ones out. 0.05, 0.10, 0.15, 0.20, 0.25, and 0.30. Okay, so the first one we have around 9%, 9.9%, so around 10%. Let me just kind of bring it up to there. No shame. Looks good. Next one, 27.1%. Yeah. 31.9%. That's going to be above the 30%, so like that. I don't know how. Oh, it's closer to 32, right? So probably more like that. 30. The 3 is 20.8%. It's around 21. 8%, 8-ish percent, 8.1%. A little more than halfway between 5 and 10. Okay. 1.9%. So 2. Yeah, you have to be good at working within scales of numbers and stuff and just like fractions of values. 0.02%. That's less than 1%. We're looking really small to the point that that's 7. I'm not going to do anything for the 7. So there's my histogram. So this was part B and part C. I think those were the only parts, so we're not being asked to interpret anything after. So just kind of laying it out as we see it. All right, there it is. That's it for that problem. Let's keep moving forward. Let's look at number 18. Got to move the circle down though. Boop, boop, boop. How do you see it? Complete the probability distribution for the random variable x. What is the probability the value of x is greater than 2? So if it only runs everything 1 through 4, it looks like 0 is not even included. I don't think this is necessarily situationally speaking as far as like you're asking a certain number of people. This could be numbers on a spinner. All right, let's copy and paste that. Here's the thing, your probabilities must add to 100%. So if this is everything involved, right, this probability of 4 is going to be 1 minus the probability of 1, probability of 2, and probability of 3 added together, right? And I know I'm overstating what it is we got to do, but that's 1 minus 0.1 plus 0.3 plus 0.4. 0.1 plus 0.3, that's 0.8. So 1 minus 0.8, which is 0.2. So we got 0.2 that goes there. What's the probability the value of x is greater than 2? So these guys, probability x is greater than 2 is probability of 3 occurring plus probability of 4 occurring. Probability of 3 is 0.4, probability of 4 is 0.2, that's 0.6, which is 60%. I don't know which one they're going to want, 0.6, 3/5, or 60%. That's it. 4 more questions. Number 19, making an argument. The binomial distribution shows the results of a binomial experiment. Your friend claims the probability P of a success must be greater than probability 1 minus P of a failure. Is your friend correct? Explain your reasoning. based on this breakdown, because it leans more toward the left side than it does, it kind of right skews there. It leans more toward the left side than the right side. Or is that left skew? I forget which way we say it. Anyway, it's favoring that left side. That's favoring percentages that are less than 50%. So I would say your friend's incorrect here. Or my friend. Sometimes I say your friend. This when I'm remembering, I say my friend. My friend is incorrect. Because the distribution more so favors values less than 50% of the distribution. No, of the spread. I don't really know what to say. The probability of success P. I wouldn't say is likely, but it is. It is less than 50% also. Therefore, P is less than 1 minus P, because 1 minus P needs to be more than 50%, right? These need to add to 100% in this case. So your friend is incorrect in that way. My friend. Number 20, thought-provoking. Scary. There are 100 coins in a bag. Only one of them has a date of 2010. You choose a coin at random, check the date, then put the coin back in the bag. You repeat this 100 times. Are you certain of choosing a 2010 coin at least once? Explain your reasoning. No. No, you could... No. In fact, that chance is... it's 1 out of 100 chance. But no. Absolutely not. You could choose it every time, but that probability is low. But no. You are not certain of choosing the 2010 coin at least once. although the probability although the theoretical probability would make it so that it could happen. It could and probably would happen. In fact, I'm going to show you what the probability would be when it says at least once. Making probably would happen. And in fact, you could choose it all 100 times. I'm kind of speaking to you as I'm typing this. All 100 times. There is just no guarantee that in experimentation it will happen. I don't know. My explanation is just saying you're not certain because you're not certain. Things in theory and things in practice are two different things. I could do it 1,000,000 times. That doesn't mean I'm going to land on it. Especially because they said you replace it. So every time it's that 1 out of 100 thing. So here's the idea, right? The probability of getting the 2010 at least once is 1 minus the probability that you don't get it at all. No 2010. So what's the probability of 2010? That's 1 minus, and we can do 100, choose 0. You have a 1/100th chance of getting it, but we're going to get it no times, and then you have a 99% chance of not getting it. We're going to look at that 100 times. Your chance of getting it at least once should be pretty decent. So I'm going to do that. Let's do 1 minus 100. This time I'm going to use this, not your Binomial PDF stuff, so you can see it in play. 100 choose 0 times 0.01 raised to the 0 power times 0.99 raised to the 100th power. It's decent. You have a 63% chance, 63.4% chance of getting it. That's pretty high. So that's why I said in this thing here, 63%. That's why I said you probably would. It probably would happen. You just need to get it once. So you have a chance. But no, there's a chance you don't. Right? That's the idea. There's a chance that you don't. So yeah, that's it. If there's a 63.4% chance that you're going to get it at least once, that means this part that we didn't see, the complement, there's a 36.6% chance that you don't get it at all. That's it. I don't know if they wanted me to do that extra, but I wanted to show you. All right, 2 more questions. Number 21, modeling with mathematics. Assume that having a male and having a female child are independent events. And the probability of each is 0.5. Part A, a couple has 4 male children. Evaluate the validity of this statement. The first 4 kids were all boys, so the next one will probably be a girl. Well, the events are independent, so this statement's invalid. This statement, let's see. First 4 kids. I mean, listen, in all of our minds, including statisticians and people like myself, will say, surely the next one will be a girl, right? That's the thing. It's leaning more that way. That's not statistically how it works, assuming everything's independent. This is an invalid conjecture, as each event is independent and the likelihood is still equal. Now, that doesn't mean, so, you know, what is the chances that this happened to begin with? Low. But now that it's happened, right? That's the same thing with like me playing roulette. What are the odds that it's going to land on black 6 times in a row? Not likely, but now that we've done it 5 times in a row, well, that 6th one is still the 50, well, not 50%, but it's as equally as likely as red. So anyway, there's that. Yeah, invalid. That's part A. That's the answer. Part B. What is the probability of having 4 male children and then a female child? This is very specific to that order. That order matters. So I'm just going to do, I don't even know if this is binomial distribution anymore, because it's not like having the female child first counts as one of these things. So I'm going to go straight into probability of 4 boys, then 1 girl. This one you don't do, as far as I'm reading it, it says then. I'm not going to do the combination portion of this. We're just going to do 0.5 raised to the 4th power, having the 4 boys, and then having the 1 girl, 0.5 raised to the 1st power. There's no 5 choose 4 or whatever you want to say there. It's just this. So that's 0.5 to the 5th. Listen, I can do this. This is 1/2 to the 5th power. This is 1 over 32. I can tell you that it's going to be that value. It's going to be really close to like 3 or 4%. So 1 over 32, 0.03125. So 3.125%. If it's just that amount. Now, having 4 boys and 1 girl as a whole would be higher, because there are different arrangements that you can have of that. It would probably, I think it would be that times 5. I think it would be close to 15 or 16%. But just this right here, 4 boys and then 1 girl, pretty low. I actually expected it to be lower, but pretty low as a whole. Part C, let X be a random variable that represents the number of children a couple already has when they have their first female child. So before they have their first female child. Draw a histogram of the distribution of P of X for 0 to 10. Describe the shape of the histogram. So, okay, this is a low set. Let me copy and paste everything to the next page, just because I need to use the lines when I do my histogram. So bringing this guy over, they're really making us play ball here. So X, P of X, etc. We're going to split this up into 10 parts. 11 parts, actually. Because the 0 is one of them. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in this case here, this is having no children before having your first girl. Basically, this is having your first kid being a girl. And then your second kid being a girl. So it's kind of, you know what I mean? That 1 is how many children you had before having a girl. I think couple already has when they have their first female child. Yes. So it's going to skew, I believe, 1 or 2. Like, this is going to be the most likely. And then it's definitely going to go down a lot. You're not going to have 10 boys before having your first girl in all likelihood. It's just going to get lower and lower. So listen, I'm going to go straight to my binomial stuff in my calculator. I'm not going to spit out all the formulas for you guys. So let's go to it. I'm going to do 10, 50% likelihood, and X, and delete all that. And let's go to the numbers. I'm going to go 2 decimal places. That's really all I can fit. Listen, this is about a 0% chance. 0.00. I'm not going to fit anything else. 0.01. Oh. Wait a second. Am I doing this right then? Because this likelihood wouldn't make any sense here. 5. Hold on. Did I write this right? I see. Let me think about what I was just saying with this one. Hold on. This might not be the distribution I want to get. Let me think about this. Okay, I thought about it. You know what I need, or you know what I don't need? I don't want this to be a binomial. I want this to do what I was doing before. I don't want the combination portion of this. That's what's making it center toward... I was thinking, why is it centering toward 5 boys before you get a girl? But that's because the binomial, the combination portion, I don't want that. So what I want is just 0.5 raised to the x and 0.5 raised to the 1 minus x. I want to make sure... Hold on. Raised to the 1 minus x. Because that's what I did last time, right? I want to make sure that I'm counting this for the first one being boys. Well, the number of things. I think... No. Let me think about how I want to do this then. Let me keep thinking on it. Sorry. Let me think on it. So I'm thinking more about it. All right, so 2 things. Number 1, I had 1 minus x on here instead of 10 minus x. But now I'm just thinking more about it. I'm thinking too much on the binomial distribution part when it's not a binomial distribution as a whole. We just saw the problem exist before. Let me go back to this. We saw the problem exist before right here where I said this was when we had 5 children. But that was specific for 5 children. This has to be specific for the number of children you have before having a girl. So this x is just going to increase over time. You want to do, in the first case here, you want to do, you don't have any children yet, but then you have your first girl. You have a 50% chance there. And then here is, you had a boy. So let's see, you didn't have any children yet, times you had a girl. And then you had a boy, there's a 50% chance there, and then a girl. And then you have 2 boys, and then you have a girl. So it keeps going like that to the point that my formula is kind of like, I think like an x plus 1 deal. An x plus 1 deal on there. So I'm going to go back here. This should be an x plus 1 in this scenario where it's you have your first child, there was a 50% chance of that, whatever, or you didn't have any children, and it moves on from there. I think this will increase. There we go. That makes more sense there. So this is the likelihood of having... I think. And I think it just shrinks, right? You have your value, right? What's the probability? You take half of it, take half of that, take half of that. So this makes more logical sense in what we're going to do. So I'll write this as 0.5. I guess I shouldn't do any rounding here then. At least not soon. 0.25, 0.125. Okay. 0.0625. So it's not a binomial distribution. It's not really any distribution because it increases over time. This isn't, the number of trials is increasing each time as well. That's the part that's tricky. This isn't one single bit. This is hard to write on my end. I shouldn't write this as a table. 0.03125. Yeah, so here's what I'm writing right now. I don't know if this is helpful for anybody. Let me maybe write sideways or something like that. Let me do the table the other way. Hold on, I'm going to fix it. Okay, I'm going to do it like this instead, and I'm going to type them out. So I'm just going straight into it. So here I have 0.5. Should I put a 0? 0.25. 0.125. And so on. All right, let me fill this out. I'll pause and I'll come back. Okay, I'm fully filled out from this guy right here. I use the, these guys right here. That's scientific notation. So I'm fully filled out. That's the table. And we got to draw a histogram. So listen, a table wasn't required, but the histogram is, and getting these numbers out is an important aspect of that. So let me get rid of this one that I was doing. Let's kind of keep this one here. Maybe I can shrink it. Yeah, okay, totally cool. Let's just use this on the side while we build out a histogram from that. Now the most common, well, 0 was the most likely one, and after that it kind of leans itself down, but it still works. So let's go to highest is 0.5, so that works totally here. So 0.1, 0.2, and they're going to get pretty small pretty fast. 0.3, 0.4, 0.5. We take half of what we had last time. So this is P of X, and here's X. All right, finally glad that I've kind of cracked the problem here. See, it makes sense to anticipate certain answers before they actually happen. Otherwise, you might kind of screw yourself over. All right, here's 10. Okay. All right, so they look equal enough width to me, even though they're not perfect. So at 0, we have 50% chance. And at 1, it's half of that, 25%. And it's literally half of the previous one each time. So, and then half of that is 12.5%. Halfway between, well, that's here. That's a quarter of the way from 10 to 20. And then 6 point... I'm just going to make them look like half of the other thing, pretty much. Sorry if it kind of doesn't work that way. All right. 3.125, so third of the way. Yes, yes. And eventually it's going to shrink to almost nothingness here. So, did what I could. At that point, let's see if that kind of makes sense that I can't really fit anything else meaningful after that. 6 is 0.7%, and then 0.3%, which is, you know, this is 1/10 as is, or this is 10% as is. I don't think you're going to be able to see anything from that. So there's the histogram. Now they're asking you the question, you know, describe, what do they say? They say, describe the shape of the histogram. This is a right skew. So it skews off to the right like that. It's a right skewed graph. I believe in the IM1 book, because that's probably where they'd ask you to come up with that kind of stuff. You describe those things. That's when you do mean, median, mode, stuff like that, and you probably come up with the names of skew, symmetrical, things like that. All right, last question, number 22, critical thinking. Well, if that wasn't critical thinking, then... An entertainment system has n speakers. Each speaker will function properly with probability P, independent of whether the other speakers are functioning. The system will operate effectively when at least 50% of its speakers are functioning. For what values of P is a 5-speaker system more likely to operate than a 3-speaker system? Okay, so we're going to have to do 2 different tests with those on for what values of P. It says at least 50% of its speakers are functioning. So I'm trying to decide how we want to say that as a whole. It's a binomial thing for sure. What I'm trying to think about is when they say the 50%, because that's not probability of success. So we have to find that, what values of P. So we have a 5-speaker system. We don't know probability of success, but we know Q is going to be 1 minus that P. And we're going to test some things with K. We need this probability thing to be greater than it. It says what values of P is a 5-speaker system will likely operate then. It's N speakers. I'm sorry, N is not 5. K is 5 in this case. So N is N. No, yeah, 5-speaker system. So there's that one. What I have to think about is whether we're doing cumulative, because there's like probability of exactly 0. The system will operate effectively when at least 50% of its speakers are functioning. So we need to know. So 50% of its speakers. In this case, half of 5 is 2.5. So you need probability of at least 3 speakers functioning. So we need probability of 3 speakers functioning, probability of 4 speakers functioning, probability of 5 speakers functioning. We need this to be greater than 50%. Greater than 0.5. 0.5. So for that to work, our N... I mean, I have my own version with my calculator thing to work it out probably better. And I don't know if this is more so... I guess it's more so trial and error. that we do there. Let's do this, because the cumulative distribution function will allow me to do this. We can also do 1 minus the probability that k is less than or equal to 2, because greater than or equal to 3, or sorry, less than 3, I should say. So less than 3. So that's 1 minus... See, I don't know how to do this in a way that you're going to do this very fancifully unless there's a lot of guess and check, and I'm not going to play... I ain't going to play ball that way unless I have my specific numbers. You know what? Okay, forget it. I'm not going to do cumulative. I am going to use my equation thing, and I am going to plug in some values here. So here's what we have. We have basically an n choose k times probability raised to the n power times 1 minus probability raised to that power there, plus n choose k here. You know what? There might be a way to do this that's algebraic. I'm wondering if it's worth venturing in that, because this would take a little bit of time. I'm going to explore and see if there's kind of an algebraic way of doing that. But you go all the way to the 5th power for these things. That's quite a bit. I don't know if it's worth that. So we're going to add those 3 up. And here's the thing. Hold on. I want to do as much algebraically that I can and see if it's worth it. This part, guys, look to fast forward on this thing if you'd like to, or whatever else. I'm just going to play with this in a live recording format. So I'm going to do 5 choose 3. I should know it, but whatever. 5 choose 3 is 10. So 10 times p cubed times 1 minus p squared. That's p squared minus 2p plus 1. Plus, I know 5 choose 4 is 5. 5 times p to the 4th times 1 minus p. Plus, 5 choose 5 is 1. 1 times p to the 5th times whatever. So this is going to be, if I distribute this, that's 10 p to the 5th minus 20 p to the 4th plus 10p cubed plus 5p to the 4th minus 5p to the 5th. This actually might work out in an algebraic way that I can actually solve this, plus p to the 5th. I need this to still be greater than 0.5, by the way. So, okay, maybe it's not so much guess and check, but at least I have a function I can work off of this thing. And I'm curious if I'm doing this right. I don't know. 10p to the 5th minus 5p to the 5th plus 2. That's 6p to the 5th. Negative 20p to the 4th plus 5p to the 4th is negative 15p to the 4th. And then I have a plus 10p cubed. Nothing there can factor. Well, p cubes can factor. So p, let's put it this way. P cubed and 6p squared minus 15p plus 10 has to be greater than 0.5. I need to get p values that'll make that so. Can that inside part factor? I don't know if that's worth venturing. Let's see. P and P. Let's try 3 and 2 with, say, 5 and 2. Negative, no. I don't think this is factorable. I don't think that something's going to add to 15 here. 10 and 1. No. 6p and 1p. 10. Oh, that would have been really close. I could have used... No, they don't have a common factor. No, I don't think that's factorable. Anyway, I want to go to my calculator now. What I'm going to do is find the value that makes this greater than it. So I worked out some things to get into this. I hope I didn't mess up any formula stuff. I'm turning a p into an x. I factored that out, and I have 6x squared minus 15x plus 10. And I'm going to go and check my table and find out what value... Oh, I need numbers that are between 0 and 1. 0 and 1. And I'm going to go by 1% increments here. When is this number 0.5 greater than 0.5? What probability of success for each individual thing? I probably could have done this a little bit differently. Oh, it's at 0.5. What? That's weird. Okay. So PSB, wait, what did they say? For what values of P is a 5-speaker system more likely to operate than a 3-speaker system? Ooh. I don't even know if I answered that question. Well, this P would have to be greater than 0.5 as a whole for this to work. I don't know if I'm doing this right. Let me check on the other version if I use these things added together. 5 choose 3, 5 choose 4, and 5 choose 5. 5 choose 3 times x cubed times 1 minus x squared plus 5 choose 4 times x to the 4th. Where's x? X to the 4th times 1 minus x to the 1st plus 5 choose 5 times x to the 5th and whoops and 1 and 0. Okay, so that's fine. I'll just kind of get rid of that part. All right, let's see if that has the same values in the table. Yeah, it does. So I did my algebra right there. So anyway, probability would have to be greater than, probability of success for each speaker would have to be there. So for what values of P is a 5-speaker system more likely to operate than a 3-speaker system? That's the part I don't know how to answer yet. I still have to do the 3-speaker system version of this. Let me kind of truncate what I have in all these things. So that was all for 5-speaker, but now that I know what I'm doing on it, I think, I want to move forward for that. So that was, I don't know if I'm doing that right though. The 0.5 that I used was applied for the amount of speakers I put in here. So now I'm saying greater than 0.5 for that. Maybe that's not what I was supposed to do. Maybe I was supposed to do 0.5 on that part. So let's leave off this 0.5 part for now. At least let me diminish what it looks like. I don't think I'm supposed to be comparing to 0.5 at the end. I think my goal is to use the 0.5 for the number of speakers that need to be working and then look at the percentages in the breakdown of the model. So let's ignore that part for now. Let's look at a 3-speaker system and do the same thing. Now for a 3-speaker system, you need to have 2 or more speakers working. So for a case where n is 3, now the probability of k being greater than or equal to 2, right? 2 or 3 speakers need to work in that case. You can't have 1 or 0. That's less than half. So that would be probability of 2 plus probability of 3. So in this case, we're going to be doing 3 choose 2 times some p to the second power times 1 minus p raised to the first power. At least these numbers are small and there are less of them. And then 3 choose 3 times p cubed times 1 minus p to the 0. Whoopsie, that should be out here, but that doesn't matter. Times 1 minus p to the 0. P to the 0. So let's expand that. 3 choose 2 will be 3. That's 3p squared times 1 minus p plus 3 choose 3 is 1. That's 1p cubed. So distribute that. I get 3, and I'm reaching the bottom of my page, but 3p squared minus 3, this is critical thinking, minus 3p cubed plus 1p cubed, which is 3p squared minus 2p cubed. If I kind of want to deal with this in like other terms, negative p squared can factor out, and I'm left with a 2p minus 3 inside of there. I don't know if it's worth kind of having one versus the other there, but I'm going to first start by comparing these in a table, and then I want to see if there's another way. Maybe I can put them together. It's just a p cubed. Oh, it's p to the 5th. Not sure. Let me put this in another table thing and see how it compares. So let me go to my graphing calculator. Let me take out this second one that I wrote, and let's write in negative x squared. I don't think there's a reason for me to factor. Actually, no. I don't think there's a reason for me to factor in this scenario here. But I'm going to compare these. 2x minus 3. Let's see. They said, when's a 5-speaker system have greater probability? So see how these are different. So what values of P is the 5 speaker system greater than the 3? You can see it's not greater right now. Now, when we hit 50%, they each hit 50% there, and then it becomes greater. So when P is greater than 0.5, that was the answer before, but that was for a different reason. P is greater than 0.5 seems to be the case where this has that change. And when looking at the table, it works out that way. So I used a version of the table to make that happen. So I'm saying 0.5 in that way because of the table comparison. What you could also do in this situation is, let's take this version of that and this version of that. I want to take both of those. Let me copy and paste them. I need to see when one's greater than the other. Hold on. Copy and new page. I'm almost done. I believe in my answer. I have conviction in it. I want to see when, for what, without needing to factor, because now they're just compared to each other, when this one here is greater than that one there. What values of P makes this greater than that? So if I bring it all to one side of the equation, I add this over, that's 12P cubed. I subtract this over, that's 3P squared. When is this greater than 0? Here's what's cool. I actually might be able to solve this algebraically. I can factor out a 3P squared, and I'm left with 2P cubed minus, oh, you won't notice, so this is IM2, so you won't know to solve this algebraically, but that's okay. Minus 5P squared plus, this is my own enrichment, 4P minus 1 is greater than 0. What we do is we set a boundary thing where we set it equal to 0. So 3P squared, 2P cubed minus, minus 5P squared plus 4P minus 1 equal to 0. So for boundary points, either 3P squared equals 0, so P squared equals 0, P equals 0. What just happened? So P equals 0 there. Or, this is the one I want to look at, 2P cubed minus 5P squared plus 4P minus 1 equals 0. Now, in terms of solving this can't factor by grouping, so I'd have to use the rational root theorem. And we can look at values of P and Q. We already know the answer is 1/2 for one of them, so my P's over Q's. This is not something you should understand for IM2, by the way. This is me exploring it myself, saying it's possible to do without a table. By the way, you could go to a table, you could compare these like that and figure out which one's bigger, or set this equal to 0 or greater than 0, figure out when it becomes positive. There's that as well. So P's over Q's is plus or minus 1 over 1 or 2. So that's plus or minus 1 or plus or minus 1/2. And I test 1, I get 2 minus 5, negative 3, plus 4 is 1, minus 1 is 0. So 1 works. So I can use synthetic division on 1 and get 2, negative 5, 4, and negative 1. I get 2. Sorry about this. I'm saying things out loud to fill dead air. I know this isn't something that you'd understand. So this factors into P minus 1 times 2P squared minus 3P plus 1. And that can factor into 2P minus 1 times P minus 1. So either P equals 1 or P equals 1/2. So as far as boundary points go, we have 0, 1/2, and 1. We have to find values that give us greater than 0. So which values are positive? If I test numbers less than 0 in my factored form of, I need to put the 3P squared in here as well. 3P squared. Let me rewrite this. Of 3P squared times P minus 1 squared times 2P minus 1. When is this greater than 0? When I plug in numbers less than 0, I get a positive, positive, negative. So this bit is negative. When I plug in a number between 0 and 1/2, I get positive, positive, less than 1/2, negative. When I plug in a number greater than 1/2, that's positive. These will always be positive. Let's see, this will be positive, this will be positive. The problem is you can't have P be greater than 1. P cannot be greater than 1. P can only be equal to 1. So P has to be somewhere between 1/2 and 1. So 1/2 P And up to 1, well, no, it's not positive then. Just between 1/2 and 1, therefore PSB greater than 1/2, because 1 is the boundary, P greater than 1/2 or P greater than 0.5. Okay, you can solve it algebraically. IM1 or IM2 crowd might not understand that. IM3 crowd, if you're near the tail end of things and you want to practice things, you possibly can understand that. But there's some big old work there. P is greater than 0.5 is my, to me, assured answer. All right, guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching that section of 5.6 where I did a lot more exploration at the end, and I hope I made sense of it myself, or you made sense of it as well. Watch Batman fight. There he goes. There he goes. All right, let's get some fighting on. Guys, take care. Thank you. I will see you in the next one.